Hi. So today I wanted to talk to you about covariance and correlation. This is in Chapter 9 of your textbook. So to introduce this idea, first let's say that we want to determine a value of Q that it's calculated from some measured values, x, y. You can't measure it directly, Q. You have to measure x and y and then calculate Q from your values of x and y. So this is fine. This is pretty standard. We are going to take n measurements of these xy pairs and calculate n values of Q from those xy pairs. And then what we want to do is get the best value of Q. So what we're going to do that, let's say, is take our average value of x and our average value of y and then calculate Q from those average values. So this is what we get. We have Q bar, which is our Q, is the value of Q calculated from our x and y averages. And then we want to put some kind of uncertainty along with that. And so we're going to calculate our variance. Remember that the variance is the square of your standard deviation. Okay? So the variance, the square of the standard deviation, is defined this way. 1 over n times the sum of qi minus q bar squared. Okay? So that's what we calculate. This is all fine. There's no issues there. But now, let's assume that our uncertainties in x and y are small and random, so that we can really approximate that each xi value is pretty close to our average value, as are our yi values. They're pretty close to our average values of y. So what we can do then is do a Taylor series expansion of Q, our calculated Q value, about our average values of x and y. Now to remind you, just in case you've forgotten, you can use Taylor series expansions to approximate a value as long as the differences between all your values and the value about which you're going to expand, in this case our average values, as long as they're small. Okay? In that case, a Taylor series expansion is defined as it's defined here. F of x is approximately equal to f of a. A is the value about which we're expanding here, plus the first derivative of your function with respect to x times x minus a plus the second derivative of your function times x minus a squared over 2 factorial, and then the sum goes on and on. So that's a Taylor series. But we've got a function of 2 variables, not just one. In the definition of Taylor series I just showed you, it was just the one variable x. We've got 2. And we're only going to keep up to first order terms because we're going to assume, like I said, that xi is pretty close to x bar. So if you squared it, xi minus x bar squared, or cubed it, then those terms would very rapidly go to 0. So we're just going to keep first order. In that case, then our values of qi could be approximated as our average value of q, which is q of x bar, y bar, plus our first derivative of q with respect to x, that's going to be a partial, times xi minus x bar, plus partial q with respect to y, yi minus y bar. This is what we're going to use. This is our Taylor series expansion. And now, we're going to plug that into our definition of our variance. So we have our variance is equal to 1 over n times the sum of qi minus q bar quantity squared. And now we plug in what our Taylor series expansion was for qi into that definition. And we get this kind of complicated looking function that we have right here for sigma q squared. Okay? Now, the nice thing is that there's a couple of terms in this very complicated thing that are cancel out. Remember that we have the q bar here, and we also have a q bar in our definition of qi from our Taylor series expansion, and those two things subtract out. And so we're just left with these partials here, these partial terms in our definition of our variance. Okay? So sigma q squared is equal to 1 over n times the sum partial q with respect to x times xi minus x bar plus partial q with respect to y times y minus y bar, that whole bit squared. All right? So that's our variance definition. Now, we can complete this square. We can do this square. And if we do that, we get this really awful looking thing here. Okay? I'm not even going to recite it. It looks horrible. There's partials squared everywhere. There's xi's squared. There's partial q with respect to x times partial q with respect to y. It's nasty. But if you remember, let's look at this term. We have this 1 over n times the sum of xi minus x bar quantity squared. Well, that's just our standard deviation of x squared, or our variance in x, so I can plug in for that. And I can also plug in my variance in y into that term, and that gets plugged into my definition for sigma q squared, our variance for q. But we still have this horrible looking term right here where the partials of q with respect to x and y are multiplied times each other. Okay? Now I'm going to take that horrible looking term and I'm going to give it a new name. And that new name is going to be called the covariance. Okay? So the covariance, sigma x sub y, sigma xy, is equal to 1 over n times the sum of xi minus x bar times yi minus y bar. That's going to be my covariance. And now, if I take that and I plug it into there, then I have something that looks a little less horrible, right? Okay, not much, but a little less horrible. Now, what have I gained here? Okay, so if we think about our covariance, I'm going to lay out the following things and I'm going to try and explain it to you. If and only if the measurements of x and y are independent of one another, then your covariance is going to go to 0 for large values of n. And if your measurements of x and y are dependent on each other, then your covariance will not go to 0 for large n. Okay? Now, let me explain that a little bit. When I say that x and y are dependent or independent, what I mean is that x isn't causal or correlated to y. All right? So this would mean, for example, let's just make it really simple and say that we're measuring the time of flight for a ball, and then we're measuring the range for a ball. Okay? Now those two things are actually going to be related to one another. Okay? Longer time of flights for a ball do lead to longer ranges for the travel of a ball. So those two things are not independent of one another. Large values of one are going to lead to large values of another. Okay? However, there are variables which are independent of one another. Okay? There's plenty of examples that you could think of for this. But let's go back to our ball example for just a little bit. If I look at my definition for my covariance again, what I have here is you see xi minus x bar times yi minus y bar. Let's think about my ball. Let's pretend for just a second that x is my range and y is my time of flight. So that if I have values of my range that are larger than average, then that also means that my time of flight is going to be larger than average. So xi minus x bar times yi minus y bar is going to lead to a positive number. Okay. Now, let's think about what would happen if my range and my time of flight were shorter than the average. In that case, xi minus x bar would be a negative number, and yi minus y bar would also be a negative number. Now, let's just say that we summed over a large value of n of all these things. Then I'm going to get a whole bunch of positive terms, because I have a negative times a negative leading to a positive, and of course a positive times a positive is a positive. So I'm going to have some large non-zero value for my covariance. And that's because x and y are dependent on one another. Okay? Now, on the contrary, if x and y are independent of one another, then the values of x aren't going to influence the values of y. So just because x is positive, that doesn't mean that y is going to be positive, and vice versa. In that case, the terms in this sum are just as likely to be positive as negative, and your sum, x sigma xy, will go to 0. So your covariance goes to 0 for values that are independent, and your covariance goes to some other value, some non-zero value, if your variables are dependent on one another. So by calculating your covariance, you can tell whether your values x and y are related or if they're independent. If you have a significant non-zero value of your covariance, then we say that the values x and y are correlated. Okay, so this is the definition, the mathematical definition of correlation. Now, I'd like to point out something. If we look at our value, sigma q squared, our variance in q, then let's say that x and y are independent, and so our covariance goes to 0. Then we can say that the sigma q squared is equal to partial q with respect to x squared times sigma x squared plus partial q with respect to y squared times sigma y squared. Now, if you remember, and if not, you can please go back and look. In Chapter 3, we talked about propagation of error, okay? And we had multiple different functions for all kinds of ways to propagate error. But we also had a general multivariable function for propagating uncertainties, okay? And if you remember, if we only had two variables, this is what it would look like. Okay? So in that definition for the propagation of uncertainty for a multivariable function, there is buried the hidden assumption that your variables are independent of one another. If your variables are not independent of one another, then that propagation of uncertainty equation, that won't hold, and you have to go back to the one here above it. Right? Just something to think about. Okay, so what are we going to do with this correlation? Okay, how are we going to work problems with it? How is it applied? First of all, in order to get to that, I want to define the Schwarz inequality. Okay, so I'm going to lay it out there, and I'm going to say the following. All right, I'm not going to prove it. I might leave that for you. But it can be proven that your covariance, sigma xy, the absolute value of your covariance, is less than the standard deviation of x times the standard deviation of y. Okay, so I'm just going to lay that out there and say that that's true. Let's then define what we're going to call the coefficient of linear correlation, which is most commonly known as the variable r. Okay. So r is going to be equal to my covariance, sigma xy, divided by the standard deviation of sigma x times sigma y. Okay? And that's this nasty looking thing here. All right? Okay, so if we use the Schwarz inequality and hold that as true, then basically what we're saying is that r is going to be a number that's always going to be between -1 and 1. Okay? Now, what does that mean? Let's think about the equation for a straight line. Y is equal to a plus bx, which we talked about when we talked about linearly square spinning. Okay? Now, here we have yi minus y bar, which is part of that definition for our variable r. Okay? If we plug that in, assuming a straight line, then yi minus y bar is going to be a plus bxi minus a plus bx bar. Your a's cancel out, and then you're left with b times xi minus x bar. So let's plug that into our definition for r. Okay? So remember, our definition for r is here. Those 1 over n's on the top and the bottom, they cancel out, which just leaves the sums with the residuals in there. Okay. So now plugging in for yi minus y bar in my equation, I get this funny looking thing for r. b times the sum of xi minus x bar squared divided by the square root of xi minus x bar squared, that sum, times b squared, and then the xi minus x bar squared again. Now, if you look at that, you've got b squared there, and the square root of b squared, that's absolute value of b. So on the top and the bottom here, you have b over absolute value of b. Now this is going to give you r is equal to plus or minus 1. Okay, it's just the way it is. So what does this say? This says that the closer that r is, your value of r, to 1 or minus 1, then the better fit your data is to a straight line equation. So if r is very close to 1 or minus 1, then this means that your data are what we call linearly correlated. All right. So I want to use this as an example problem so that you can understand the significance of this. So the example problem that I've chosen is this. Now don't worry, I am the professor and these were scores from my classes, but they were taken from a long way back and you don't know these people and I haven't given you their names, so it's okay. So let's just assume that there's 10 students from a class and the students have the following homework and exam scores. And you want to know if doing well on your homework is linearly correlated to doing well on your final exam. Okay? So here's the students 1 through 10, and here's their exam scores. And this is out of 100%. These are percentiles, so some of them did pretty miserably. Okay, sorry. And then here's their exam scores also laid out for you. Okay, so there's the values. So now let's calculate our coefficient of linear correlation to see if doing well on your homework is correlated with, linearly correlated with doing well on your final exam. All right, so I did this in Excel, all right? In column A here, I put the student number, and then I put their homework score next to that in column B. And then in column C, I put their exam score. Now, I'm going to need the values of X bar and Y bar, their homework score average and their exam score average. So I went ahead and did that. I'm sorry, I have an itchy nose. I went ahead and did that here. So I calculated the sums and the average here. All right. Now, in my definition of R, it asks for xi minus x bar values and yi minus y bar values. So once I calculated my homework score average and my exam score average, I went ahead and calculated those differences in columns that I'll call E and F here. Okay? Now, in my sum term here, what I have to do on the top is multiply the residuals for x times the residuals for y. So I did that in this next column, and I called it e times f. And then on the bottom here, I have to calculate the square of my residuals for x and y, and I did that in the e squared and f squared columns. Then I have to sum up those values. I have to sum up the residuals of x times the residuals of y, and I have to sum up the residuals of x squared, and I have to sum up the residuals of y squared. And I've done that here in this row, which I called sum. Okay? And then I use those sums to calculate my value of r according to the formula here at the top of this page. And I get a value for r of 0.78. Okay? Now remember, r is going to be a value that's between -1 and 1. And the closer that r is to 1, or -1, the more correlated, linearly correlated these things are. So here I have positive 0.78. That means that 0.78 is pretty close to 1. It's not too bad. So that means that, yes, doing well on your homework does indicate that you're going to do better on your exam. At least it's correlated with that. Now, how do we really numerically quantify what R value with some sort of confidence value? So there's a table in your book that does this. Okay, it's table C in your appendix. I'm going to show you with this problem how to evaluate what we've got. So the column here, this first column, N, that is the number of measurements that you've taken in your stat. Okay, N. So for our case, we had 10 students in the class, so N is equal to 10. Now, across the top row, you have values of R naught. Actually, it's the absolute value of R naught, okay? Absolute value. So our value was closest to 0.8, 0.78, 0.8. It rounds to that. So now if we go over to the 0.8 column and then down to the 10 row, then what we read off is 0.5. Now, what does that mean? Okay. Well, in Table C, what it tells you is a percent confidence. Okay, so this is a percent confidence that x and y are not correlated. Okay, not correlated. So what this means is that there's a 0.5% chance that your homework score is not correlated to your exam score. And that means that there's a 99.5% chance that your homework score is correlated with your exam score. So good odds, okay, based on this data. Now, also, you could get negative values of R. Remember that I said that the values of R had to lie between -1 and +1. If your value of R is negative, okay, then that means that the two values are negatively correlated. For example, all right, paying taxes and being happy, negatively correlated, all right. You can still use your table to evaluate whether or not they're correlated. All you have to do is take the absolute value of your R value and then read the table off. And then that's the percent chance or the percent confidence that those two variables are negatively correlated. Now, I want to caution you about something. First of all, correlation does not prove causality. Okay? Just because you do your homework doesn't mean necessarily that you're going to get a good exam score, okay? You have to go the extra mile to prove causality. Most of the time, advertisers and politicians don't do this. They don't go that extra mile. They just throw these stats up there, show they're correlated, and call it a day, and call it causal. But this is a dangerous thing to do. There could be other things that cause the underlying effect that you desire, right? Like getting a good exam score. There could be other causes for that that don't have anything to do with doing your homework, and you'd have to do an in-depth study to make sure that's true. Now, this is a pretty simple example, but I want to show you something that I used to mislead my students a little bit in Physics 1150 and 1151. Okay, so one day the students kept coming to me and asking me, what can I do to get a better grade in your class? What can I do to get a better grade in your class? Okay, well, the short answer was study, right? You could study. That would help a lot. But what I did instead, because I had said that and they weren't leaving me alone, what I did instead was to throw up a bunch of plots in class one day and show all the things that they could do. Basically, the underlying message was still study, right? But what I was really doing was showing them all these different ways to cause my true desire, which was for them to study. So I threw up all these examples. One of them was they had to do these hand-in problems. Now, if you went back and calculated, the hand-in problem was only worth about 1.75% of their overall grade. So a lot of them weren't doing it. This was a mistake on my part, which I have since fixed. But the fact of the matter is that doing the hand-in problem is really studying, okay? Even though it takes a certain amount of your time, it improves your grade. So what I said was, well, you need to do your hand-in problem. Look, here's the hand-in average from a previous year. Here's their average on the hand-in problems, and here's their final grade. Here's the linear regression of that, and the linear correlation coefficient is 0.76 for a sample size of this bit. That's 99% correlated. So if you do your hand-in problem, you'll do better on your final grade, right? Even though it's only a very small percentage. What that really means is that these people that were doing their hand-in problem were studying, right? Now, the underlying cause, though, is not doing the hand-in problem. Like I said, the hand-in problem is only 1.75% of the overall grade. What was the root cause was that the students that did their hand-in problem were the good students. They were the ones that went that extra mile. They were the ones that did the extra work, even though they didn't necessarily have to do it to get a good grade, right? That's what's causing them to get a good grade. Okay? That's the underlying cause. There's little sleights of hand like this that go on all the time in advertising and in politics, and so you need to be aware of this, and you need to think about it when you're be a good consumer. Okay? Be a wary consumer. This is used all the time. Another thing that I want to caution you about is that sometimes the linear correlation coefficient isn't all that useful of a statistic. I see this all the time in Physics 4210 and senior seminar. Students will do an experiment and they'll do a linear fit for their data, and they'll put that correlation coefficient value up there like it's something to be used and thought about, and wow, that's interesting. No, no, no. Okay, not necessarily. For example, one of the senior seminar experiments for a long time was the photoelectric effect that Albert Einstein won his Nobel Prize for in 1905. And the photoelectric effect says that, you know, if you have light incident on a surface, then you can calculate the energy of that light. Then that light causes photoelectrons to be ejected from the surface. And here's the equation that relates it. The energy of light, HF, is equal to the kinetic energy of the photoelectrons that are ejected, plus your work function. The work function is how much energy it takes to get that electron to be freed. Okay? Now, Einstein did this a long time ago. We know that the frequency is linearly correlated, or linearly related, to the kinetic energy of your electrons. So, putting that up on a plot for an R value of 0.98, saying, wow, these were really linearly correlated, not new, not useful, okay, and not really what we were trying to get you to prove. What we were trying to get you to do with that experiment, for example, was to determine the Planck's constant, right? They were trying to measure Planck's constant and get an uncertainty on a known constant that way. That's what we wanted. We wanted them to do that. We know they're linearly correlated. That's not useful. Linear correlation coefficients are used when you want to know if things are linearly correlated or not. So they're used lots of times in medical studies, they're used lots of times in psychology studies, psychiatry studies, things like that, when you're not really sure if things are related or not. That's when it's most useful. Okay, so that's the difference between correlation and causality. That's the definition of your linear correlation coefficient R and the definition of your covariance sigma xy. Hope that helps, and I'll see you in class.